Section 4.4, Concavity and Curve Sketching. We talked about when a function is concave up and concave down. See here that when the derivative, the second derivative, or the first derivative is decreasing, that means second derivative has a negative sign, then it's concave down, or like I said, it spills water. And then when the second derivative is positive, it's concave up, or it holds water. So the graph of x cubed is concave down from minus infinity to 0, and it's concave up from 0 to plus infinity. So just the definitions that we talked about in class, that a function is concave up on an open interval if f prime is increasing on that interval, and it's concave down on an open interval if f prime is decreasing on that interval. So what is the second derivative test for concavity? It says that if the function y equal to f of x is twice differentiable on an interval, okay, then if the sign of the second derivative on that interval is positive, then it's concave up. And if the sign of the second derivative is negative, then the graph of f on that interval is concave down. So wherever there is a change of sign of the second derivative, so that is where a point of inflection occurs. If we look at these two graphs, we have that the sign changes from concave down to concave up. And we did this in class. We took the first derivative. So y prime is equal to 3x squared, and then y double prime would be 6x. And of course, if we want to look at the signs of the second derivative dividing the number line by 0, because when we set this equal to 0, that becomes a critical value. So to the left of 0, if you plug in, say, -1 on the x, 6 times -1 is negative. So y double prime here is negative. And then to the right of 0, y double prime is positive. So a change of sign from negative to positive makes x equal to 0 a point of inflection. And there it is, where we have a concave down and concave up. So x equal to 0, and of course when we plug it back into the original function, then y is also 0, so that at the origin 0, 0 is a point of inflection. Okay, and then if we look at this parabola, the first derivative is 2x, the second derivative is 2, which is constant, it's always positive. So on the whole interval, it's concave up. So there is no point of inflection on the graph of the parabola y is equal to x squared. It's always concave up on the whole real line. We already did this in class, found the point of inflection from the interval from 0 to 2 pi is at pi. Okay, you can go back to your notes and check on taking the first derivative, second derivative, set it equal to 0, and then test the critical value to the left of pi and to the right of pi, because we found that the critical value occurs at x equal to pi when we set the second derivative to 0 to look for points of inflection. Also, at a point of inflection, it's either the second derivative is 0 or it fails to exist. Okay, here is where we did this again in class, where when we took the first derivative, it'll be equal to 5/3 x to the 2/3, and then taking the second derivative, when you set it equal to 0, it does not exist at x equal to 0, but it's still a point of inflection when we tested the sign from the left of 0 to the right of 0. Again, check your notes where we did this in class. Here, There is no point of inflection when y is equal to x to the fourth, because it's always concave up throughout the real line, throughout the number line, from minus infinity to plus infinity. X to the 1/3, again, we take the first derivative, second derivative, set it equal to 0, and we found that y double prime at 0 is undefined, so we can still, that is still a critical value, and we tested it on both sides, to the left of 0 and to the right of 0, and we found that it's concave up. The function y is equal to x to the 1/3 is concave up to the left of 0, and it's concave down to the right of 0.